Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of engineering chemistry. We'll dive into key concepts like phase diagram of single component system, water, phase diagram of binary eutectic system, COAG. Slide 1, phase diagram, introduction. Alright, let's begin by understanding what a phase diagram is. A phase diagram is a graphical representation that shows the states of a substance under varying temperatures and pressures. It essentially tells us what phase, solid, liquid, or gas, a substance will be in under specific conditions. Now, why is it important? It helps predict how a substance behaves when conditions like temperature or pressure change. For instance, water at 1 atmosphere pressure boils at 100 degrees Celsius, but at lower pressure, it will boil at a lower temperature. Phase diagrams are crucial in material science, metallurgy, and chemical engineering because they guide us in understanding the thermal stability of substances, alloy formation, and phase transitions. Key components of a phase diagram. 1. Phases: solid, liquid, and gas. These are the main states of matter that a substance can exist in. 2. Phase boundaries, the lines separating each phase. They show the points where two phases coexist. 3. Triple point, this is a unique point where solid, liquid, and gas phases coexist simultaneously. For water, this occurs at 0.01 degrees Celsius and 0.006 atmospheres. 4. Critical point, beyond this point, the distinction between liquid and gas phases disappears, and a supercritical fluid is formed. For water, this is 374 degrees Celsius and 218 atmospheres. 5. Eutectic point, the temperature and composition at which two or more components solidify simultaneously. This is more relevant to binary systems, as we will discuss in slide 3. Significance example. If we want to prevent steam formation in a boiler system, we need to ensure that the pressure and temperature remain within the liquid phase boundary. Otherwise, steam generation may lead to pressure buildup and potential hazards. Slide 2. Single component system, water phase diagram. Now, let's focus on a single component system using water as an example. A single component phase diagram only considers one substance, so it is simpler than a binary system. Phases of water. Solid, ice, exists at temperatures below 0 degrees Celsius under standard pressure, 1 atmosphere. Liquid, water, exists between 0 degrees Celsius and 100 degrees Celsius under standard pressure. Gas, steam, exists above 100 degrees Celsius under standard pressure. Key points in the water phase diagram. 1. Triple point, 0.01 degrees Celsius, 0.006 atmospheres. This is a unique combination of temperature and pressure where ice, liquid water, and steam coexist. 2. Critical point, 374 degrees Celsius, 218 atmospheres. Beyond this point, water and steam become indistinguishable, forming a supercritical fluid. 3. Melting point curve, this boundary line separates the solid and liquid phases. 4. Sublimation curve, this curve shows the transition from solid to gas, bypassing the liquid phase. 5. Vaporization curve, the boundary where water changes to steam. 6. Significance in boilers, by knowing the vaporization curve, we can prevent steam formation at undesired points, ensuring safe boiler operation. 7. Example, if a steam generator operates at 200 degrees Celsius and 150 atmospheres, it is in the supercritical region, meaning water behaves more like a dense gas than a liquid. Slide 3. Binary eutectic system, COAG phase diagram. Now, let's move to a more complex system, the binary eutectic system using copper, Co, and silver, Ag. A binary system involves two components, making the phase diagram more complex but also more useful in alloy design and metallurgy. What is a binary eutectic system? A binary eutectic system shows how the temperature and composition of two components affect the phases present. In our case, we are dealing with copper and silver. Key components in AICTE diagram. 1. Liquidus line. Above this line, the alloy is completely molten. 2. Solidus line. Below this line, the alloy is completely solidified. 3. Two-phase region. Between the liquidus and solidus lines, we have a mixture of solid and liquid. 4. Eutectic point, 779 degrees Celsius, 72% Ag, 28% Cu. This is the lowest temperature where the alloy solidifies simultaneously into two distinct solid phases, a Curich phase and an Agrich phase. 5. Eutectic composition, the specific composition that solidifies at the eutectic temperature. 6. Solid solution regions, areas where one component is dissolved in another. Application example. In soldering, the eutectic composition ensures that the alloy melts and solidifies at a fixed temperature, preventing partial melting and maintaining the structural integrity of the joint. Slide 4. Eutectic point and its significance. Now, let's focus on the eutectic point in more detail. Definition. The eutectic point is the composition and temperature at which two or more components solidify simultaneously from the liquid phase. It represents the lowest temperature at which the liquid phase can exist in equilibrium with solid phases. For Ag system, the eutectic composition is 72% Ag and 28% Cu, and the eutectic temperature is 779 degrees Celsius. Why is the eutectic point significant? 1. Predicts alloy behavior, ensures uniform solidification, crucial in preventing phase segregation. 2. Low melting point, useful in applications like soldering, where rapid solidification is desired. 3. Structure control, produces fine-grained microstructures, enhancing mechanical properties. 4. Precision in casting, provides a well-defined melting point, ensuring consistent processing temperatures. 5. Cost efficiency, reduces the need for high-temperature processing. 6. Prevents cracking, eutectic alloys have fewer phase boundaries, reducing the risk of thermal cracking. 7. Example. A Ag alloy used in electrical connectors relies on the eutectic composition for precise melting and solidification. Slide 5. Differences, single component versus binary eutectic systems. Now, let's understand the key differences between a single component system and a binary eutectic system in a clear and simple way. Number of components. In a single component system, we deal with only one substance, like water. In a binary eutectic system, we consider two components, such as copper and silver. Phases present. The single component system shows three basic phases: solid, liquid, and gas. In a binary eutectic system, we see multiple phases, including two distinct solid phases and a liquid phase. Triple point vs. Eutectic point. A single component system has a triple point where solid, liquid, and gas coexist. A binary eutectic system has a eutectic point where two solid phases solidify simultaneously from the liquid phase at a specific composition and temperature. Application and complexity. Single component systems are simpler to analyze and are often used to understand basic phase changes, like water freezing or boiling. Binary eutectic systems are more complex and are widely used in alloy manufacturing, soldering, and metallurgical processes. Examples. Single component, water at 0.01 degrees Celsius and 0.006 atmospheres exists as ice, water, and steam. Binary eutectic, Ag alloy at 779 degrees Celsius and 72% Ag solidifies as a eutectic mixture of two solid phases simultaneously. This differentiation helps us understand why studying both systems is important. The single component system simplifies phase changes, while the binary system is vital for understanding alloy behavior and applications.